So some people asked for extra help on how to draw Lewis structures. So let's draw some Lewis structures as some practice. Now, a Lewis structure is a structure where you have atoms represented as letters or symbols. So like this would be sulfur, and let's say we had oxygens all around it. Lewis structures tend to have lines that represent the bonds, which are the electrons being shared between two atoms. So that line I just drew are the electrons being shared between that oxygen and that sulfur. Same thing with this oxygen and sulfur, this oxygen, that oxygen. So those represent bonds. Lewis structures also tend to have the little dots that come in pairs, often pairs, but not always, around some of the atoms, which are called lone pair. And those are the electrons that are not bonding. These are called unbonded or something like non-bonding electrons. There's multiple different names for them. But this is an example of a Lewis structure. Now, Lewis structures can have double bonds like this. Lewis structures also sometimes have charges. So if you were to calculate the formal charge, there'd be a negative over here and a negative over here. It's 0, 0, 0. I forgot to remove those extra lines. So Lewis structures are basically going to look something like this. And here's how you draw them from scratch. So first, you'll typically be given a formula. So if we were given this formula, SeCl2, so that'd be selenium dichloride, then you have to have your periodic table ready. So if we go to photo library and go to favorites, we can add a periodic table. And on this periodic table, one thing that's critical for being successful with drawing Lewis structures is recognizing how to count the number of valence electrons. So we are going to use the middle part, that's the D block, or the F block. We're going to focus really just on the tall columns, the main group elements. The first main group has one valence electron. And then the second main group has two. Skip the middle, and then you have 3, 4, 5, 6, 7. Helium only has 2, but everybody below helium has 8. Helium's tiny, so it can only hold 2 electrons in its outer shell, but all the others below it can hold 8. So that's the first thing, is simply being able to count the columns, the tall columns, the main group element, and determining how many valence electrons it has. So if we were to draw SeCl2, we would recognize that selenium is in the sixth tall group. It's in the same family as oxygen and sulfur. So all of them are going to have 6 valence electrons. So we're going to count them up to start off with 6 plus. So we've already taken care of the single selenium. Now chlorine is over here in the 7th tall group. And that means that it has 7 valence electrons. But notice how there's 2 chlorines. So I need to multiply the 7 by 2. And when we do this, we get 6 plus 14, which is 20 valence electrons to use in our bank when we're drawing this. We don't really need the periodic table anymore once we have that part straight. So let's get rid of that. And also get rid of this. So in our electron bank, so to speak, we can draw 20 valence electrons. Those are the 20 electrons that are going to be on the outer shell of these atoms. So here's what it looks like. Get rid of this as well. That's just helping us get to that number. So we have 20 valence electrons. The first element is typically in the middle, but not always. So we have selenium here. It's an educated guess that we would put selenium in the middle and the 2 chlorines would be on the outside. Sometimes it's not that clear, and with practice you'll get more about which one's in the middle. Oftentimes instructors will tell you which one's in the middle when it's not clear. For example, in this element, or in this compound, HCN, H is not in the middle. H can't be in the middle, so C is in the middle. And the structure actually starts off looking exactly like the formula does. H with some space for the bonds, C with some more space, and then N. So you'll just get practice with determining what's in the middle and what's not. So far we have selenium. We're going to plop that down. After you count up your valence electrons, which we've already done, then you put the symbols for the elements on the paper or on the screen, whatever you're using. So I have selenium here, and we said that that's going to be the central element. So we're going to put our 2 chlorines around it. Those, I call that the naked atoms. You put the atoms on the paper. They're naked because they don't have any electrons or anything around it. They're just symbols on the paper waiting for something to happen. Now, the first step after you do all that, so I guess it would be the third step, would be you need to actually bond them all once. And every time you draw a line to that central atom from one of the outside atoms, you use 2 electrons because every line, every bond is a pair of electrons. So if I draw this line here connecting the chlorine to the selenium, I just used 2 valence electrons. Now I need to connect the other chlorine in the selenium, so that's another 2. I drew 2 lines, I just used 4 electrons to do that bonding. So far, I have used up 4 of my 20, and that gives me 16 remaining. So that's 16 valence electrons left. What do you do with those 16 valence electrons? Well, you spread them out around the outside atoms. The outside atoms are the chlorines. The first thing you do with these remaining electrons after you've bonded them all once, so we've done the bonding once, and we have a leftover amount, that's when you spread them out around the edges. So let's do that, and they do go in 2 by 2. So of my 16, I'm putting down 1, 2, 3, 4, 5, 6, go to the other side, 7, 8, 9, 10, 11, 12. I've used up 12. I still have some left over. A matter of fact, that's going to be 4 valence electrons left. So you use them all up on the outsides. What we've done so far is we've satisfied the octet rule for those outside atoms. This chlorine on the left has 8 electrons touching it. 2, 4, 6, 8. Same thing with the chlorine on the right. So they can't hold any more dots. The max that they're going to typically hold is going to be 8, unless it's something small, in which case hydrogen, for example, is going to only be able to hold 2. So once hydrogen has a line touching it, you don't add any dots to it because hydrogen's tiny. It can only have 2 electrons touching it, as opposed to other atoms, which can have up to 8. And in the future, you'll learn more about central atoms, which can have more than 8. Some of them. So what do you do with these 4 remaining valence electrons? You can't put them around the chlorines anymore, but you still got to put them on the paper. You're going to put those 4 remaining valence electrons on the central atom, also in pairs if you can. And there we have it. We've used up those remaining 4 electrons, and now we have none. So I'll move this down for space. And we are at 0 valence electrons. Your goal is to always have 0 valence electrons left after you count it down from how many are available all the way down to 0. You want to use them all up. They all exist in the structure. So we're done with that. We've reached 0. And then you're looking at this structure and you're like, okay, that's it. This is it. This is a 2-dimensional structure. You can't see it now, but when you learn about VSEPR theory, you'll see that this is actually a 3-dimensional structure because those lone pair are going to take up space, as are those 2 chlorine atoms, and you'll have a shape called bent, sometimes also called angular. So that's how you do that one. That's the Lewis structure for selenium dichloride. Now let's do another one. Let's say we have a compound or a molecule that is NO2 minus. This is a nitrite ion. They don't always have pluses and minuses, but in this case we have an ion. That is going to affect how we count. So if you look at the periodic table, you'll find that nitrogen is in the 5th tall column, so it's going to have 5 valence electrons, and there's just 1 nitrogen. There are 2 oxygen atoms, so I'm going to multiply 2, and every oxygen has 6 valence electrons. So far, this is an odd number. This is 5 plus 12, which is 17. But then we have this little negative sign, which also means that there's an extra electron added. Remember, electrons are negatively charged, so if there is a negative sign, you add in an electron. If it were a positive sign, you would subtract an electron. But in this case, it's a negative sign, so you add in an electron. So we have 6 plus 6 plus 6, which is 18 valence electrons in total. That means that we're going to use 18 valence electrons when we draw our structure. So we can move that up here, or I guess over to the side so we can use it for counting. And let's plop down the N in the middle, and then the oxygens on the outside. Remember, you do need to bond them once, at least. So to do that, you're going to connect the O to the N in the middle, and then the other O to the N in the middle. We drew 2 lines, which are 2 bonds. Every time we draw a line, we need to subtract 2 electrons. So we drew 2 lines, we need to subtract 2 times 2, which is we just used up 4 of our valence electrons. That gives us 14 valence electrons remaining to put on this paper, or on our structure. Let's spread those 14 electrons out. 1, 2, 3, 4, 5, 6. The left oxygen is now full with its 8, so the 6 we just added plus the 2 in the bond. And we have 7, 8, 9, 10, 11, 12. We just used up 12 of those valence electrons. Now we only have 2 valence electrons left. Where do you put them when you don't have any more space on the outside? You put them on the inside. So now this nitrogen also has a pair of electrons, which we call a lone pair. We just used up those, and we have reached 0, which is the goal. So we have 0 valence electrons left in our bank, which is available for us to draw. We have them all on the paper. So we can get rid of this because we don't need it anymore. Everything is accounted for on the paper. Now, if you're looking at it, you might be thinking, okay, well, the left oxygen has 8 valence electrons. 2, 4, 6, 8. The right oxygen has 8 valence electrons as well. And nitrogen is one of those elements that is going to typically need to follow the octet rule. It needs to have 8 electrons touching it. Remember, the electrons in a bond are being shared. So these electrons in this green line are belonging to this oxygen on the left, but they also belong to the nitrogen on the right. So this nitrogen here has 2, 4, 6 electrons touching it, and we needed to have 8. That means that one of these oxygens, it doesn't matter which one you choose, is going to have to donate, so to speak, a pair of electrons toward that bond to kind of give it some, to kind of, I guess, share with nitrogen in the middle. So let's say that we have these electrons here from this left oxygen. Doesn't matter which ones you choose, but I'm just showing you in this case. That'll create a multiple bond. In this case, it'll be a double bond. So whenever you draw another line, you have to remove a lone pair of electrons because you don't want to add any electrons to this page. If you actually count them all up, we have 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons, just as we said we should have. So in order for me to draw a line, I've got to get rid of a pair. So let's get rid of those electrons and create a multiple bond. Now we have a double bond between the nitrogen and the oxygen. If you had chosen to use the other oxygen, that's okay. That actually creates like a resonance structure. But it doesn't really matter which one you pick because you can flip this molecule around and then it's the other oxygen. To make this look a little neater, what we typically do, but it doesn't have to be this way, is you can rearrange the dots to make it look a little bit better. For example, this oxygen on the left, I can put the lone pair like this, and then I have my double bond with the nitrogen, and then a single bond with the other oxygen, and that would be my Lewis structure. So that's how you do Lewis structures. Sometimes you always need to count up the number of valence electrons, and you need to put them on the inside when you run out of space on the outside. Sometimes that central atom is still not going to have an octet if it's one of the ones that needs it, like nitrogen does. So if it doesn't have an octet, then you need to pick one of the outside atoms and share in to create a multiple bond. Sometimes it needs to happen more than just once.